Hello, everyone. Today, we're going to present the results of using cloud programming models to improve the utilization of supercomputing systems. Modern HPC systems suffer from severe resource underutilization. When it comes to CPU resources, we find out that the number of idle nodes fluctuates. And when we queried the Slurm batch system on the PSDane supercomputer, we find out that many of those nodes are idle for less than 20-30 minutes, which means that they cannot be used by the batch system for long-running jobs because the allocations are always static. Furthermore, a lot of memory is left idle simply because the nodes are over-provisioned to support high memory jobs. And finally, other researchers have found out when studying the GPU utilization that many jobs are purely CPU and they cannot use the accelerators that are already on the node. At the same time, other jobs might want to use more GPUs, but they cannot allocate more nodes because they would be left with a lot of CPU resources that they cannot use. This means that to improve the utilization, we need systems that provide fine-grained access to resources, and at the same time, they allow for short-term allocations. The problem in HPC systems is that our current architecture is very coupled. We have homogeneous nodes where we have an accelerator in every node, a lot of memory, which works great for homogeneous jobs. We never pay the access latency to use more resources. We can try to improve the utilization by allocating different workloads, but as other researchers have found out, this is not an easy task because of the resource compatibility and performance interference. At the same time, in the data center, we see the trend towards using disaggregated resources, which makes sense from the utilization perspective. We only use the resources that we need. The problem is that it's expensive, and it also always adds the latency of accessing remote resources. We propose a new approach that deploys to existing HPC systems with the same architecture, but provides a software layer to allow for fine-grained access to resources. To that end, we propose to use serverless functions. Functions are very easy to scale, they are fast, they have a limited lifetime, which means that we can very easily fit them into short-term availability of resources. The problem is that functions are not high performance, and they come with a lot of performance issues. To solve this problem, we use RFAS, a high-performance serverless platform, and adapt it to the requirements of a supercomputing system. So we provide the access to HPC containers like Sarus or Singularity, to accelerators, to parallel file system. We use the idle node memory to host warm containers. And the isolation provided by containers allows us to implement a safe multi-tenancy with a collocated batch jobs. And then also we allow batch systems to tell the RFAS platform when and how to use resources. And at the end, the programmers use those functions to accelerate. At the runtime, they can offload a GPU or CPU or work or maybe remote memory to other nodes by using functions. We implement our approach on 3 classes of resources: CPUs, GPUs, and remote memory. For CPU and GPU, we collocate a batch job, in our case it's Lulesh, with a function-style CPU and GPU workloads. To that end, we use NAS benchmarks and Rodinia benchmarks for GPUs. We show that when we collocated these benchmarks by running a batch job, and then at the same time running in a loop the CPU and GPU benchmarks, we show that we can significantly improve the utilization of the system. Furthermore, for the remote memory, we show that we can host a batch job running Lulesh or Milk, and then an RFAS instance that is serving remote memory to other functions. And Lulesh can support up to 10 gigabytes of remote memory operations, which is almost saturating the network bandwidth with a minimal overhead of less than 5%. With Milk, we can serve, which is more sensitive to these memory operations, we can serve up to 1 gigabyte of memory per second with overhead below 7.5%. And as a final part of evaluation, we show a Black-Scholes OpenMP application and a micro-benchmarking API to show that applications can offload computational work to serverless functions and improve. By using these cheap idle resources that would otherwise be completely unused, they can significantly improve the performance of the application and achieve speed up. Our future work will concentrate on pricing models and more workloads. Please check out our preprint code and artifact, and also our other work on high-performance serverless. Thank you.